Assalamu alaikum. This is our online lecture number 2 of EE-212. In this lecture, we're gonna learn phase plot of repeated pole. And second, we're gonna learn phase plot of complex poles are zeros. Okay, poles are zeros. Okay. So if you remember what we did in our previous class, that we took a transfer function h of s is equal to 1 by s plus 1, and we said that here in this omega n is equal to 1. Okay, you can take different values of omega n, but we for application purpose we simply take omega n equal to 1. Okay. And we draw phase of h of s. We write h of s as h of j omega, and then we said that its angle will be minus tan inverse omega. This is omega by omega n, but omega n is here, it is omega. Okay. Then what we did, that we draw a table of omega versus phase of h of j omega, which is minus tan inverse omega. Okay, and we said that we are interested here in just three main frequencies when omega is equal to omega n. Okay, omega is equal to 1 by 10 times of omega n, and omega is equal to 10 times of omega n. Okay, so for this case we find out that this is equal to 0.1 when omega n equal to 1. Okay, this is equal to 1 and this is equal to 10. Okay, and we know that tan inverse of 0.1 was what, how much? Minus 6 degree, and this was minus 45 degree, and this was minus 84 degree. Okay, then we simply draw this phase versus omega. We said that this is omega is 0.1 times up omega n, this is 1 times up omega n, and this is 10 times up omega n, and this is 100 times, and so on. Okay, now here say this is minus 6 degree, say here this is minus 45 degree, and this is our asymptote minus 90 degree. Okay. So we find out at 0.1 our angle is how much? Minus 6 degree. At 1 this was minus 45 degree, and at 10 this was minus 84 degree. Okay, and we simply connect these points like this. Okay, and this will reach to this minus 90 degree when omega approaches to infinity. Okay, then we draw phase plot for h of s is equal to s plus 1, which was simple 0, and this was nothing but just change this angle from minus to plus. Okay, this becomes 6 degree, this will become 45 degree, and this become 84 degree, and asymptote will be how much? Plus 90 degree. Okay, so we just need to flip this along this omega axis. Okay, and we can draw, say this is plus 90 degree, this is our asymptote, so this will, we will flip and we will draw this like this. Okay, so this is for simple 0, and this is phase plot of simple pole. Okay, this is what we did in our previous lecture. Okay, now we are in a position to move to this phase plot of repeated poles. Okay, what we mean by this repeated poles? Okay, repeated pole means that you have a transfer function of this form. H of s is equal to 1 by s plus 1 square. It means that you have a pole at s plus 1 and you have another pole which is s plus 1. Okay, it means two poles are lying at same point. Okay. Now we are interested in finding angle of h of j omega. What will be its angle? Okay, for this purpose, this is simple. I know you will understand, but we will go to the basics how we can find angle of this thing. Okay, if you have two say complex number given, say r1 and multiply r2. Okay, say this is equal to z. Z is equal to r1 into r2, and you know that r1 is a complex number. Okay, of this form x plus jy, and r2 is also a complex number which is x plus jy. Okay, so we can write this as r1 amplitude with angle theta, and this will be r2 amplitude with angle theta, and you know that r1 is equal to r2 because both are x plus jy and x plus jy. Okay, so if r1 is equal to r2, okay, so this angle will be theta. This is say theta 1 and this is say theta 2, so theta 1 is equal to theta 2 is equal to theta 1. Okay, so we can simply write this equation as r1 square with angle theta 1 plus theta 2, and theta 1 is equal to theta 2 is equal to theta, so we can write as this is 2 theta, right? Now look at this equation. What is this? This is a complex number, r1 r2. Okay, and r1 is equal to r2. Okay, so what will happen to angle of h of j omega? H of j omega will be angle of this one thing. This is minus tan inverse of omega. Okay, multiply by what? 2. Okay, so we can write it this way, that this is minus 2 tan inverse of omega. Okay, this is our angle h of j omega, right? Remember one thing, that I normally write j omega this way. Okay, but in standard text you will find this as j omega small j, because this capital J in electrical engineering denote current density. Okay, so avoid this thing, but I write it here because I have some difficulty in writing this thing. Okay, now you understand what happening here, that this power determine this multiplying factor. Okay, so if you have a transfer function of say this form, h of s is equal to 1 by s plus 1 power say r. R could be any number. This could be 1, this could be 2, this could be 3, this could be 4, any number. Okay, so we can simply write this way, that angle of h of j omega will be minus r time tan inverse omega. Okay, where r is equal to could be 1, 2, 3, 4, 5, 6 and so on. It could be any number. Okay, so this is how you can find phase of repeated poles. Okay, so we'll take a example, we'll solve this example and we will find a plot of this one, and at the end of the lecture I'll give you one or two example as a home assignment, and you will solve them at your home. Okay. Now we proceed with the same example. H of s is equal to 1 by s plus 1 whole square. Okay, this is a simple one, so that's why we will start with this and we'll proceed further. Okay, what will be angle of h of j omega? This is minus 2 tan inverse of omega. You remember that omega n is equal to 1 here. Okay, this could be anything. This could be 1, this term, this could be 1, this could be 2, this could be 3, this could be 0.5, any value. Okay, so here in this particular example this is 1. Okay, now we need to plot this phase with respect to this omega. Okay, so again we are interested only in 3 frequencies. So we form that table which we draw for in our previous case. Okay, so this was our previous case. So now we draw this table again for repeated poles. Okay, so I told you that we are only interested in 3 frequencies. Okay, the first one is when omega is equal to omega n. Okay, omega n here is 1. Okay, then 1 omega is equal to 1 by 10 times of omega n, which in this case will be 0.1, and then omega is equal to 10 times of omega n, which is 10. Okay, so here this angle minus tan inverse of 0.1, this is minus 6 degree, then multiply by 2, this is minus 12 degree, this will be minus 90 degree, and this will be minus 168 degree, right? You can just compare that we had this minus 6 degree, minus 45 degree, minus 84 degree, so we simply multiply this angle by 2 because we have now 2 poles lying at a single point. Okay, now you just need to plot this table. Okay, so here we have omega, here this is 0.1, this is 1, this is 10, say this is 100, and so on. Now what will be our asymptote? Yes, because each angle is multiplied by 2, so our asymptote will also multiply by 2. So before this was minus 90 degree, now this will be minus 180 degree, right? So at 0.1 before this was minus 6 degree, now this is what? 12 degree. At omega equal to omega n, this was minus 45, now this will be minus 90 degree, right? And at 10 times up omega n, this was minus 84, now this will be minus 168. Okay, so 168 will be somewhere here. Okay, you just need to draw these points together. Okay, and this will touch this minus 180 asymptote at infinity when omega approaches to infinity. Okay, this is how you're gonna plot when you have repeated poles. Okay. Okay, now what will happen if you are given a repeated 0? Repeated 0 will be of this form: h of is equal to s plus 1 whole square. Okay, so the procedure remains the same. You just need to flip this along this omega axis. Okay, and you will draw this, and this will touch this asymptote for this will be plus 180 degree. Okay, so this is how you're going to plot repeated poles. Okay, so you can note it down one home assignment. Okay, that what will be phase plot for h of s is equal to 1 by s plus 2 whole square. What will be phase plot for h of s is equal to 1 by, say, s plus 5 whole square. Okay, try this at home. Also you can find s plus 2 whole square as well. Okay, same way s plus 5 whole square. Okay. So this is your home assignment. Just solve it. Okay, you don't need to submit it, but just for practice you can use and solve this. Okay, also you can refer to your book and solve different example over there. Okay. So this was first part of lecture number 2, which was repeated pole. Okay, now we can start working on complex poles. Okay, so we know that if a transfer function is given, say h of s is equal to omega n square over s square plus 2 zeta omega ns plus omega n square, and we are interested in finding out and plotting angle of h of j omega. Okay, we are interested in this thing, that how can we plot angle of this type of transfer function. Okay, so we can simply write this whole transfer function this way: h of j omega is equal to omega n square over s square. Okay, so s is equal to what? J omega. So we can write it as j omega whole square plus 2 zeta omega n into j omega n plus omega n square. Okay, you know that j square will give you minus omega square. Okay, so this will be, we can write this and this combined, this will be a real number, so we can write it this way: omega n square over omega n square minus omega square, okay, plus j 2 zeta omega n into omega. Okay, now if you pay close attention to this transfer function, you will see that this is our real part and this is our imaginary part, because it contains this j component. Okay, and we are interested in finding out what phase of h of j omega. Okay, so phase of h of j omega will be minus tan inverse imaginary part, which is 2 zeta omega n times omega over omega n square minus omega square. Okay, this is your phase. Okay, now we need to plot this thing against omega. Okay, remember that our plot is nothing but we are plotting our transfer function phase with respect to omega. It means we have an axis omega and we have another axis h of j omega, and we are plotting one against the other. Okay, so we'll have different values of omega. Okay, and we will have different values of corresponding phase, and we just draw those points together. Okay, but if you pay close attention to the phase of your transfer function, omega n is a constant. Okay, so we have two variables, one is omega and one is zeta. Okay, if omega n is constant, our phase will change by changing omega as well as changing zeta. Zeta will also change and omega will also change this values. Okay, value phase. Okay, how it gonna change? So I'll show you one table. Okay, that how this angle will be changed. Okay, so pay close attention to this table. This table. See, when zeta is equal to 0.02, okay, and omega is equal to 0.1 times of omega n. It means that in a previous case, what we did that we took omega is equal to, we were interested in 3 points, right? 1 by 10 times of omega n. Okay, so we are just looking just single this point. Okay, so when omega equal to 1 by 10 times of omega n, okay, phase of this thing, this transfer function, this will be minus 0.2, okay, at this value when zeta is equal to 0.02, okay, then phase tan inverse 2 zeta omega n times omega over omega n square minus omega square. This will give you an angle of minus 0.2 degree. Okay, you understand this point, right? Now if we change zeta from 0.02 to 0.05, we increase zeta. Now if we have zeta value omega equal to 1 by 10 times of omega n, we are not changing this value. Okay, we are only changing zeta from 0.02 to 0.05. Okay, then this phase will be minus 0.6 degree. Before, for 0.02, our angle was minus 0.2. This is now 0.6 degree. Okay, the point I want to make here is that you are changing zeta, okay, and omega is same. Okay, so for same value of omega, you have different phase angles. Okay, when zeta is equal to 1, your angle will be minus 11.4. This is nothing but approximately equal to minus 12 degree, as we did in our previous case. Okay, so you are changing just zeta values, omega remains the same, but your angle, corresponding angle is changing. This tan inverse 2 zeta omega n times omega over omega n square by minus omega square. This angle is changing. Okay, so for each transfer function you will have different zeta values. Your phase angle will change accordingly. Okay, so we take simple example. Say we have a transfer function h of s is equal to, say your transfer function is of this form. H of s is equal to say 10 over a square plus 6s plus 10. Okay, you have this transfer function, and you need to draw h of j omega. Okay, phase of h of j omega. Okay, so you simply need to find out what will be value of zeta here. Okay, what will be value of omega n. You just need to find those two values. Okay, and how you find these two values is you compare this equation with your standard equation, which was you compare this 10 over a square plus 6s plus 10 with your standard equation omega n square over a square plus 2 zeta omega n s plus omega n square. So clearly we can see that omega n square in this case is 10. Okay, and 2 zeta omega n is equal to 6. Okay, so you have only these values. Okay, you can easily find out what will be omega, and let's say we change this to 100. Okay, just for simplicity, so we will get omega n is equal to 10. Okay, so now what will be zeta? Zeta will be 6 divided by 2 omega n, which is 20. So 6 by 20. Okay, you can find exact value 6 divided by 20, and this will be something this will be this will give you the result 6 by 0.3. Okay, this is 0.3. So you have omega n, you have zeta. You can find out h of j omega. Phasor h of j omega, which was tan inverse 2 zeta omega n times omega over omega n square minus omega. Right? Now you give different values. Okay, this is your final equation, and here zeta is 0.3 and omega n is 10. Okay, so we can transform this equation into a table where we can plot omega versus phase of h of j omega, which is nothing but tan inverse, okay, 2 zeta omega n omega over omega n square minus omega square. Okay, and obviously here you will put a minus sign because this was in pole. This is simple pole. Okay, complex pole. Okay, now we draw this table. Okay, so you have zeta value. Zeta is equal to 0.3 and omega n is equal to 10. Okay, you can write this again, minus tan inverse 2 multiplied by 0.3, so this will be 0.6 multiplied by 10, so this will be 6 omega over this is omega n square, this is 100 minus omega square. You just need to put different values of omega over here. Okay, so let's say as we did in our previous case that we were interested just in 3 frequencies. Okay, so now if omega is equal to 1 by 10 times of omega n, okay, so what will be phase? You just need to put this as 1. Okay, because our omega n is what? How much? 10. Okay, so you just need to put omega is equal to 1 here. Okay, so you can find out this value, 6 over 100 minus 1 is what? 99. Okay, and find tan inverse minus tan inverse of this value, you will get some angle. Okay, you can find out this angle. Okay, then you can find out other values. Say omega is equal to 0.2 times of omega n. Okay, you will get some value. Then omega is equal to say omega n. Okay, and then omega is equal to 10 times of omega n. Okay, you can find out in between points as well. Okay, but I am interested just only in this point, and this point. Okay, if you pay close attention, this 6 by 90 degree, this will approximately equal to minus 0 point 3.5 degree. Okay, this will be minus 3.5 degree. Okay, and when omega is equal to omega n, okay, so this thing become what? 0, and 6 omega by 0 is what? Infinity, and tan inverse of infinity is what? Yes, minus 90 degree. Okay, so this will pass through minus 90 degree. Okay, and the higher we goes, okay, this will reach to what? Toward minus 180 degree. When omega, we increase omega, okay, like omega is equal to 10 times up omega n. This angle should be minus 170 or something, okay, approximately equal to minus 70 degree. When this is 100, this is 1000 times up omega n, or 2000, 10,000 up omega n. Eventually it will reach to minus 180 degree, okay. So you can plot this complex pole this way, that say you have this values, say this is 10, say this is 1, okay, obviously here this is 0.1, this is 100, and this is 1000, and so on, okay. So we noted that when omega is equal to omega n, this is omega n, right, in our example. So here this angle was minus 90 degree, okay. When this was 0.1, sorry, exactly equal to 1, this angle was minus 3.5 degree, okay. And here let's say this is the asymptote, this is minus 180 degree. So when we reach to this point, this will be minus 170 degree, and this will very close to this minus 180 degree, okay. So we start here, okay, we start here, and we just connect these points, okay. So remember that this line is zeta is equal to 0.3, okay. Now pay close attention that as we increase this value of zeta, okay, this plot will go straight away, okay, from this point to this point, okay, this will go straight, okay. But if we decrease, if zeta increases, this will go this way. But if we increase zeta value, okay, this plot will go this way. How? Just go back and look at your value of your phase, okay. Here this is 2 zeta. If I reduce this to say this is 0.3, right, so if this is 0.1, okay, our angle will be we reducing this zeta value, so this will be tan inverse 2 multiplied by, before this was multiplied by 0.3, now this will be multiplied by 0.2, okay. So this will be multiplied by 0.2, so this will be 0.4 multiplied by omega n equal to 10, so this will be 4, right, omega now. Before this was 6 omega, now this is 100 minus omega, okay. What we are doing, we are reducing this value. If you are reducing this numerator, okay, this plot will go up, because now this angle will reach here, okay, and the next angle will go here, okay, and you will connect this point here. This will eventually pass to this minus 90 degree, okay. If you reduce zeta furthermore, say to 0.02, okay, this will go more up, okay, these points, and this will go again and touch this minus 90 degree and then pass through here, okay. And you goes on decreasing this value, okay, say when zeta equal to 0, okay, this will go straight away, this phase will be 0, okay, and at this point this will be minus 90 degree, and this will reach automatically to minus 180 degree, and then this will continue, okay. So this is your when zeta equal to 0, okay. So just observe this neatly, this graph here, okay, that as we increase zeta, okay, we are actually increasing these angles, okay, this will go this way, But if you reduce zeta, okay, this will go up. So at 0.02, this is your plot, okay. At 1, this is your plot, okay. When zeta equal to 0, then your plot will be exactly this way. This is your exact plot, this pointed one, okay. So one thing you just need to remember here when you are plotting second order response of complex pole or first plot of complex pole, okay, this is that when you have simple poles, you are only interested in finding phase, okay, and you are plotting this against what? Omega, okay. But when you have complex poles, it means you have two things to look up for when you are plotting phase. One is omega and second one is zeta, this damping ratio, okay. And this is how it will change the phase of your plot, okay. Now you can solve these examples at home. Say you have a transfer function h of s is equal to say 5 over s square plus 2 zeta omega ns plus no. Say you have h of s is equal to 10 over s square plus 5s plus 3, okay. You can take a second example. Say h of s is equal to 5 over s square plus 3s plus 2, okay. You can take this example and you can find out its phase, okay. Remember that you just need to find out value of omega n, you need to find out zeta, okay, what will be zeta value, and you just need to use this equation tan inverse 2 zeta omega n over omega n square minus omega square. Just find this value, put it here, you will find out your equation phase in term of omega, and then you give different values to omega and you simply plot your transfer function, okay, your phase, okay. And you can also use them as a simple zeros, like of this form, s square plus 5s plus 3, okay. You can also use this as simple 0, s square plus 3s plus 2 over 2, okay. You can use it this way as well, okay. So you can find out how to plot these complex poles or these complex zeros, okay. So I hope so you understand how can we plot complex poles, okay. I'll just go to a little bit revision, okay. That if you have h of s is equal to omega n square over s square plus 2 zeta omega ns plus omega n square, okay. So you just need to remember that if you need to find out phase of h of j omega, so this will be minus 10 inverse 2 zeta omega times omega n, or omega into omega n square minus omega square, okay. And you simply need to find out what is omega n and what is zeta, okay. In each example, say I gave you this example, here you can easily find out what will be omega n and what will be zeta, okay. You just need to compare this equation with this equation and you will find out, okay, easily. So put those values over here and here, here you will get equation between omega and phase, okay. So here this is your phase. When you put those values here, your equation will look like this: omega n over omega n square minus omega square, okay. Just give different values to omega. Say first put omega equal to 1 by 10 times of omega n, then omega equal to 1 by 5 times of omega n, then give omega equal to omega n, say omega equal to 10 times of omega n, okay, and just find corresponding these values, okay. And then simply use this plot. This is your phase and this is your corresponding angle. You have given, you find out these values, so you just need to put these values over here, okay, and find the corresponding values and find the plot, okay. One thing you need to remember that this is a second order equation. So in second order equation, our asymptote for simple pole will be minus 90 degree, and for for complex pole this will be minus 90 degree, minus 180 degree, okay, and for complex 0 this will be plus 180 degree, okay. And an interesting result can be drawn from, if you are given this thing, okay, then you can say that this is asymptote will be minus 360 degree and this will be plus 360 degree, okay. And what will happen to its phases? You just need to find out single phases of these things, okay, these points, and then multiply by 2, you will get phases of this value, okay, and you simply need to draw those values, okay. So this is the end of our second lecture, okay. And after this, Dr. Amar Arshid going to continue with our third lecture, which will be in which we will cover these different types of filters, as well as how you can find out this cutoff frequencies, and your filter will be low pass filter, high pass filter, band pass filter, as well as band stop filter. I hope so we understand how to plot phase plot for simple poles, 0 at origin, pole at origin, or simple 0, or simple pole, okay, or complex poles, are complex zeros, okay. Now we understand all these points, that how we can phase plot, we can find phase plot for these kind of transfer function. Now you can combine them together and you can give a composite plot as well, okay. No need at this time. I'll send you a tutorial and you can compare your result with result run from MATLAB. You just need to install MATLAB in your laptop, okay, and I'll give you a tutorial later on, and we will draw these all thing, and we're gonna play with this thing, and you will see that it is quite interesting to draw in MATLAB, okay. This is the end. If you have any questions, feel free to ask using Microsoft Teams, as well as you have my WhatsApp contact, so you can always contact me. But official way to contact and interact with the respective teacher, you need to use Microsoft Teams, okay. Thank you.